Hey there everyone, welcome back. This is part 2 of the lesson on thermodynamic processes. And this is a separate part because I want to key in on an idea that is very near and dear to me in thermodynamics. So if I'm being totally honest with you, when I first started learning thermodynamics, I did not do very well at it. And that is because I don't think I really understood what the heck was going on and what this all meant, like what the ideal gases were doing and why any of it mattered. And I remember that all came to a head one day when I went into my lecture hall and the professor on the board drew a picture. And he drew a picture for a PV diagram. And it looked something like this. He drew 4 points on the board, A, B, C, D. And then he connected the dots, which is always fun to do. And then he proclaimed quite proudly to the class, "This is an engine." And I specifically remember sitting in the lecture hall thinking, this person's crazy. This is not an engine. This is a box. To me, this is an engine. This is an engine, like a 4-stroke engine you might find in a car, where there's 4 parts to a cycle, where you're going to bring in air and fuel, and then you're going to compress that fuel, and then a spark is going to create an explosion, which is going to drive the piston down, and then eventually you're going to exhaust it. So a 4-phase, where there's an intake phase, a compression phase, a power stroke, and an exhaust phase. And you can see this to me is an engine, because what is it really doing? Well, as a heat engine, essentially, it's using heat energy created by the explosion, by the chemical reaction of the air and the fuel to cause the gas to expand. And then that expansion is going to do work, and that's what's going to be transferred to the drive shaft that's going to allow the car to drive. So, and this is what a heat engine is. It essentially uses the flow of heat to take some of that heat energy and turn it into work. And then that useful work can be used to do things. And so to me, this is clearly an engine. And again, this is clearly just a box. And that was quite frustrating. But what I'm going to attempt to do in this video is to prove to you that actually this is an engine. This what looks like a box is in fact an engine. And so I'm going to take that on and hopefully we can be successful. So let's just think about what this means, okay? You can see that basically, I want to point out that what I've got is I've actually got a process. I've got a process that's going to start at A, and we're going to go from A to B to C to D back to A. So it is a cyclical process. So we see that from the get-go. And I want to think about what might be happening at each stage in this process as we move along, okay? So the way I'm going to envision this is I'm going to think about this as being like a piston. I've got a piston with that's filled with an ideal gas, and this piston, the gas in that piston is going to change pressure and temperature and volume as we go through this cycle. So let's think about what this might look like. Well, let's start at A. So at point A, you can see that I'm at a relatively low pressure and I'm at a relatively low volume. So I'm going to draw a piston here. And you can see that this piston is containing a volume of gas. So I've got an ideal gas in here, and those gas particles are all bouncing around. And this piston is free to move up and down, okay? And so because it's free to move up and down, it would move upwards, it would slide upwards because of the gas inside, except there is a pressure on it which is pushing down. And so I'm going to visualize that like this. I'm going to say that pressure that's holding the piston down is like, imagine I put a single weight on the piston like this. So I've got a little block, and that pushing on the piston provides the pressure, which kind of keeps it in place. And it's a low pressure, so I've only got one block sitting there, and that's what holds it in place. And so you can see here, this is what it looks like to be at state A, low pressure and low volume. So I'm going to now move through to my next phase. So I'm going to go from A, and I'm going to move along here. I'm going to move to B. So what would this system look like if I move from A to B? Well, you can see, number one, I stayed at the same volume. So the volume didn't change, but the pressure increased. So first of all, my piston is still in the same location. Okay, my volume has not changed. And so my gas particles are bouncing around inside the piston. as they do. But importantly, my pressure has increased. Well, if the pressure is increased, but the piston wasn't allowed to slide up, that would be like I came along and instead of having just like one block sitting on this, I have 3 blocks sitting on this piston. So there's more force weighing down on the piston, and so the greater pressure pushing upwards and the greater pressure pushing downwards, they kind of balance out. Now, let's think about this. The only way that could happen for me to increase the pressure, but keep the volume constant, would be if heat were to flow into this system. So in this step right here, as I go from A to B, I would have heat flow into the system, and I'm going to call it QAB. So the heat that flows in phase, in step AB. Okay, cool. So now I'm going to go from B, and I'm going to transition over to C. And you can see that in this step, as I go from B to C, I am going to stay at the same pressure, but I'm going to increase the volume. So what happens there? Well, that means that the piston must have been allowed to slide up. So as we go into step C, now my piston slides upwards. And so the particles are all bouncing around, okay? And now I've got my masses. I still got the same pressure, so I've still got the same 3 masses sitting on top, 3 little boxes sitting on top of my piston, but I've been able to slide up. Now, what must have happened here? Well, if I'm going to increase in volume, but keep the pressure the same, I want to be able to push those boxes up. Again, in this case, I must have had heat that flowed into the system. So in this case, I've got a heat, and I'll call that QBC. So heat must have flowed into it. And now those blocks are up in the air. Okay, so now we're going to go from C down to D. So I'm going to move from C to D. And you can see that as I move from C to D, I'm going to drop in pressure, but I'm going to keep the volume the same. So here I am at step D. Okay, and I've decreased my pressure, but I'm keeping my volume the same. So the piston is still elevated like that, and the gas is still inside the piston. Okay, so that hasn't changed, but I'm now at a lower pressure. So the only way I could be at a lower pressure would be if I had fewer boxes on top. So now I'm back to my 1 box on top. You can see I'm back to at point D, I'm at the same pressure I was at when I was at point A. So that in our analogy, that's just 1 box. Okay, well, so what must have happened here? If we're going to go from the same volume at a high pressure and drop the pressure down, well, now heat must have flowed out of the system. So in this step here, I had heat come out, and I'm going to call that QCD, the heat that flowed during the process, CD. And then the last step is for me to go back to A. And so A is going to look the exact same as it did before. I'm going to have a small volume, I'm going to have a small pressure, and my state I have returned to my original state. Okay, so here I've got a little box on top like that. And you can see that state A is identical to the original state A because it's the same point on the PV diagram. Now, if I go from a large volume at a fixed pressure and drop down to a lower volume, again, heat must have flowed out. So I've got one last step here where heat flows out of the system, and I'm going to call that QDA, which is the heat that flows out in that last step, DA. Okay, so what does that all mean? Well, the first thing I want you to recognize is that this was an entirely reversible process. So I started at A, went to B, C, D, A, and back to A. And so it is really important that I point out that this process that we just modeled here is what we call an ideal reversible heat engine. That 4-stroke engine that I showed you before is absolutely not an ideal engine, and this is a much simpler engine that we've created here. But it's an engine nonetheless, because heat flowed in and then heat flowed out. Okay, and that's the first requirement for a heat engine, that heat flows through it. But like, what did it do? Like, it just went through a cycle, and I ended up back where I started with, and I thought that an engine was supposed to do work. And here's the really, really important key here. It did. If you look closely at this cycle, it actually did something useful for us. And it did something useful right in this step right here from B to C. From B to C, when it took these 3 blocks and it lifted them in the air for us, that is doing work. Because you can think of it like an elevator, right? You got 3 blocks on the ground floor, and now you lifted those 3 blocks up to the top floor. Well, that's doing work, okay? You'll notice that that's not the only step that work was done, right? So work was done by the gas for us in this step right here. I'll call this work BC in that step. But work was also done on the gas in this step right here, DA. The thing to recognize is that work in this step was done on the gas because the gas was compressed. Now let's take a look at those 2 works. The thing to recognize is that when I go from B to C, I lift 3 blocks in the air. I could take those 3 blocks off at that top floor and let the gas compress, and overall it has done a net amount of work for me because the 3 blocks were brought up and only 1 block was brought down. If I keep repeating this cycle, it's a very simple analogy, but this is a machine that lifts blocks up in the air for me. Every time I go through the cycle, 3 blocks go up and only 1 block comes down. And over time, this is doing more and more work for us. The gas is doing work for us. So there's a few conclusions that are really important that we make from this. And the first one that I want to point out is that if I look at my first law of thermodynamics, which is the change in internal energy, we know the change in internal energy is going to be the heat that flows in plus the work that is done. But let's think about the change in internal energy for the whole system. So for the whole cycle, A, B, C, D, A, which is the whole cycle all the way around. Well, if I start at A and I go all the way around and come back to A, then the total change in internal energy is 0 because I begin and end at the exact same point, which means I'm beginning and ending with the exact same internal energy. So that's an important thing to recognize. But let's think about the heat flow. So the heat that flowed into the system, right? There was 2 times the heat flowed in. So I had QAB plus QBC. Those are the 2 times the heat flowed into my system. Those 2 heat flows must be greater than QCD plus QDA. Remember, those are the times that heat flowed out of the system. And they must be greater because overall, the internal energy of the gas didn't change, but it did work for us. And so where did that work come from? Well, this is the main idea behind a heat engine, that a certain amount of heat flows in and a certain amount of heat flows out, but some of that heat is diverted into work. So the heat that flows out must be less than what flowed in because the machine is doing work for us, and that's where we get that energy, okay? The last thing I want you to think about is the work itself. And again, there was 2 steps where work was done for us, or say by the gas or on the gas, okay? And the first step is in that step BC. So let's take a look at step BC. We know that the work done in step BC is negative P delta V, which we also know is just equal to the area under the curve when we go from B to C. So that would be the area. If I draw a line down from B and a line down from C, that would be the area of this entire rectangle here. So that's the work done by, done by the gas. But remember that we also did work on the gas, and we did work on the gas in step D to A. And so the work done on the gas would be the area. Work done on the gas is work dA, which again is negative P delta V, would be the area from D to A, which is this area right here, this kind of area here. And here's what I want you to notice, is that overall, the work that was done for us by this heat engine really is just the work that's enclosed by the enclosed shape. So the total work done by the machine is just the area of the enclosed shape, right? You can see that the area here in this enclosed shape, that is the net work done, right? So the work is done by the gas and the work is done on the gas, but overall, the enclosed shape is giving me my net work done. Okay. Now, last thing I want to point out here is this is very much a heat engine, and the way we can tell it's a heat engine is because this cycle goes clockwise. Because it's going clockwise, the work is done by the gas at a higher pressure and then on the gas at a lower pressure, which always means the gas is doing more work for us than we are doing on the gas. And so hopefully what you can see is that any shape, any enclosed shape on a PV diagram is going to be one of these reversible heat engines, right? Where we can go through each step, and as we go through each cycle around and around, heat flows through it and work is done by the gas for us. Okay, that is it for the lesson on thermodynamic processes.